Hello, everyone. Welcome and thank you for joining us today as we continue our IB Users Group webinar series. My name is Linda Herman. I'm the Client Relations Manager for Imaging Biometrics. Today's webinar is titled Quantitative DSC Perfusion Class Maps. This webinar will provide the background, application, and guidance on the functionality of our DSC MRI fractional tumor burden mapping technology. It is presented by Michael Schmainda, co-founder and CEO of Imaging Biometrics. We have muted the microphones and ask that you use the Q&A feature to ask questions at the end of the presentation. Today's webinar will be recorded and made available for future viewing. And now I'll turn it over to Mike.
Thank you, Linda, and welcome everyone to our IB Users Group webinar series. Today we are showcasing our fractional tumor burden mapping technology. This is an advanced imaging solution that uses two of our products, IB Delta Suite and IB Neuro, and is used to help clinicians treat patients with brain tumors. We're going to discuss the need of FTB, share some of the development history and the validation studies that have been performed, introduce you to the automated workflow, and then demonstrate to you the semi-automated processing approach using the ACAN workstation with our module called IB RadTech as a plugin. So FTB maps are an MR DSC perfusion-derived quantitative class map that can, on a voxel-wise basis, differentiate tumor from a treatment effect or non-tumor tissue. And it uses tissue-validated cutoff thresholds to help do that. It's expressed as a percentage, basically the ratio of tumor or high SR-CBV voxels to the total enhancing voxels within a region of enhancement. Before we jump into this, though, I just want to recognize two people who were critical in the development of FTB maps. Dr. Leyland Hu at the Mayo Clinic in Arizona really provided the pioneering vision, if you will, for FTB maps in collaboration with Kathleen Schmainda at the Medical College of Wisconsin and our team here at Imaging Biometrics. We validated the process and have it commercialized and packaged up and ready to go. And it really helps address major clinical gaps in brain tumor imaging as compared with conventional imaging that's currently available. Also want to add that Imaging Biometrics is the only company that offers FTB maps, and all the publications in the literature that reference or study FTB use IB software. Interesting side note, at the recent ASFNR meeting in August, a poll was taken, and the question was, have you adopted fractional tumor burden analysis? And it was interesting to see that 70% of the respondents are interested, but have not yet adopted the FTB maps. So it's very promising to us to see the growing interest, and hopefully today we can address any questions about FTB maps and help you get started at your institution. So the need for FTB maps really centers around addressing one common question that is commonly faced among treatment teams, and that is the enhancing region tumor, or is it an effect due to treatment? Here's an example of a 39-year-old male with a GBM post-resection. You can see the post-contrast image and the flare image on the left, where the region of enhancement, bright signal enhancement is shown. The patient undergoes 4 weeks of treatment with chemo and radiotherapy, and that same region explodes into a much larger area of enhancement. So the current method is to go in and biopsy and take a tissue sample and send it to pathology. Upon reoperation, in this case, the tissue came back as mostly necrotic, and that's not uncommon today using standard imaging. Here's another example of how challenging it is to distinguish progression from pseudoprogression on standard imaging. This is a case of a patient with routine surveillance scans at 1, 3, and 5 months that include T1 plus C, and you can see the region of contrast enhancement shown here at the different stages and how it's increasing. The comments from the radiologist is undeterminate. They're thinking it's either GBM progression or pseudoprogression during every time point. Even at month 5, they're thinking it's post-treatment changes. Upon redo surgery, It came back as recurrent GBM. And if you look at the RCBB maps, you can see that there is increased vascularity in that region. So standard imaging cannot really tell the story. CBB maps are tremendous help in that regard. But even then, there's a question that arises: is there a CBB threshold or value that can clearly distinguish tumor from non-tumor tissue or post-treatment radiation effect? One approach has been to determine the mean RCBV within a contrast-enhancing region. But as these slides will show you, those can also be problematic. Here's a case with 2 patients. The one on the left, you can see the region of enhancement on the T1 plus C and the corresponding RCBV map. There's a similar sized region of interest on the right, showing the region of enhancement and the RCBV map. They both have the same median RCBV and mean RCBV. So the same metrics, same size of tumor, etc. And you think they're the same type of tissue. However, when you do look at the FTB maps, the one on the left had an FTB of 42%, and the one on the right had an FTB of 82%. Well, the tumor voxels are the red areas in the enhancing region identified as shown. And as you would suspect, the progression-free and overall survival for these 2 patients varied quite differently, which corresponds much more closely with the FTB maps as compared to just the region of enhancement on the CBB maps alone. So that spatial information is critical, and it's finding its way into the operating rooms. FTB maps can be imported onto surgical navigation systems such as Medtronic and BrainLab. And here's just an example of a tweet posted by Dr. Max Krukoff at the Medical College of Wisconsin, where he imported FTB maps into the BrainLab system to help him target a site for biopsy. And he said it changed the spot I targeted for sure. So obviously, if you see here the region of enhancement, the surgeon could think that if they grab anywhere that's in the enhancements that they're going to capture a good representative sample. But the spatial information that FTB maps provide obviously can direct you to the regions of red, which corresponds to more aggressive, highly vascular tumor. So again, FTB maps consist of 2 components, a delta T1 map and a standardized RCBV generated by IB Neuro. And at the end of the day, we create a class map that shows regions of non-tumor, tumor, and indeterminate areas. I'm not going to get into the details about delta T1 maps or DSC perfusion imaging. Those were covered extremely well in prior webinars. The first delta T1 maps was covered by Professor Schmainda earlier last year, and more recently, Dr. Michael Ive from Stanford discussed DSC imaging and FTB maps in neuro-oncology. And both of those webinars are available on our website for viewing if you choose to do so. But just to remind everybody, here is an example of delta T1 maps. On the left here, you see the T1 and the post-contrast T1. And these are common inputs into any brain exam. So delta T1 maps do not require any special imaging or scanner time to collect the information. And on the output, we get a quantitative delta T1 map. The benefit of delta T1s is that you can see here on the T1 and the T1 plus C, there's bright signal on both, which makes it very difficult for even expert readers to agree on what they're looking at. However, when you look at the delta T1 map, you can clearly see that these quantitative maps make the areas of enhancement pop. They detect subtle regions of enhancement and even subtract out confounding factors such as post-surgical blood product. The second component is IB Neuro, and that's our first product that was proven to be the most robust or have the most robust contrast leakage correction algorithm. And that was published in 2008. And here you can see the distinction between tumor and reference brain, much more greater than the other methods to which it was compared. There's a lot of unique features about IB Neuro, but I want to talk about 2 of them today. The first is standardization, and the other one will be the validation studies done with tissue biopsy samples. So MR imaging is inherently variable. The same patient could be scanned on the same scanner with the same scanner settings at the same time, and the output measurements could vary considerably. There are some methods to get around this issue. The traditional approach is to use tissue normalization techniques. One is where the user will manually place a reference ROI on contralateral white matter. And the manual placement, of course, takes time, does not allow for automated processing, but it also introduces inherent variability. The user must have some knowledge as to where to place the ROI, and many users are placing the ROIs on multiple slices just to get more consistent values. The other option is to use IB Neuro, which is standardized and automated. The automated approach obviously eliminates the need to draw those reference ROIs, and studies have shown that the standardized approach is much more consistent over time. And here was a study done in 2010 by Bedeker. The normalized RCBP had a coefficient of variation of 9 to 30%, whereas the IB Neuro built-in standardization approach has a coefficient of variation of 4 to 6%. With regards to cutoff thresholds, more and more groups are using IB software to establish those cutoff thresholds, and we're glad that they're consistent when they use standardized RCBP. The first was done by Dr. Leyland Hu at the Mayo Clinic in Arizona, where he used a binary approach to distinguish post-treatment radiation effect with GBM using a cutoff threshold. And then more recently, Melissa Pra at MCW, she was the first to use a 3 classification method and the first with standardized FTB map. And an outcome of that was that this upper threshold of 1.556 was established, which identifies very aggressive tumor and very high RCBV. Other groups have been publishing using FTB maps. The Hawksworth study was the first prospective study that tissue validated that compared normalized versus standardized and showed that standardization was outperforms the normalization techniques for FTB. And then Dr. Michael Ive recently showed that FTB maps can impact clinical decision making. Finally, getting back into the operating room, here's a study published by Dr. Jennifer Conley, where the region of enhancement with the FTB map superimposed was shown here. The surgeon did a great job of removing the areas of blue, which is consistent with necrotic tissue or dead tissue, but unfortunately missed areas of yellow and red, shown here. And over time, you can see that specific area really grew in a very short amount of time, indicating that the surgeon missed this region of very vascular tumor or high growth tumor. So the cutoffs that we have built into a standard package is 1 and 1.556. We do not dictate which cutoff thresholds you choose to use, but in this case, the blue corresponds to SRCBV values less than 1.0. Red is above 1.556, and this yellow region is an indeterminate area consisting of maybe a mixture of both. So the key is that because these are quantitative, you don't change these values over time, and you can see how these volumes are responding, are changing over time, and whether the patient is responding to treatment or not. A fourth class map that I want to highlight is this orange area. The orange areas within our FTB maps identify areas where no DSC signal was present to compute, and thus the tissue status is unknown. This is a known issue with susceptibility weighted imaging, and it's not reflective of our software by any means. But if you include those orange areas in FTB totals, it could cause inaccurate measurements. So to address this issue of signal dropout, we identify them, but we don't include them in the FTB calculations. So our FTB maps are most mature in 8 high-grade glioma. That is where most of the studies have been conducted, but more recent studies also just suggest their utility in brain metastases. Again, we don't dictate which cutoff thresholds to use, but we do request or recommend that you be consistent with those, simply because our software is quantitative and you can accurately measure changes over time. So changing the thresholds would not make any sense in that case. The tissue normalization techniques are manual and introduce variability, so we recommend avoiding those. And our workflows are totally customizable, not just what cutoff thresholds to use, but the number of classifications can be modified and customized for your needs. And the colors that we apply can also be changed, although we should note that the colors chosen are colorblind friendly. Recent studies also suggest that FTB maps provide greater confidence in making clinical decision making, and because the FTB maps provide that rich spatial information, it ensures patients are getting optimal treatment decisions made for them sooner. So our automated workflow, it's essentially DICOM in, DICOM out. We have application that resides on an existing workstation, whether it's Mac, Linux, or PC, that's networked within your infrastructure. So we receive the DICOM images as another DICOM network node. We have some front-end intelligence that will identify which type of images are being received, what type of data is being received. We then execute the appropriate algorithms, and we output the maps and then output to your PACS. There's no user interface for the automated processing, so I'm just going to share some example output. Obviously, we can output the FTB map itself. We can share some things such as the histogram of the CBV values, some quality assurance output, and in this case, this is the signal time course, which shows you and gives you some confidence whether the gadolinium contrast agent was administered properly. We can also output the reports showing the enhancing region and the tumor statistics within that region for any parameter map that we can generate. We can superimpose a parameter map over anatomical, which again provides the spatial relationships. We can identify where the software automatically found the arterial input function. And then we can also provide some intermediate screen captures of the registration steps to give you confidence that the co-registration steps were performed adequately. Finally, we can create a summary report, which includes prior time points and how the tumor is changing over time. Not just how it's changing, but by how much, because again, our software is quantitative. So 3 ways to get FTB maps at your institution. One is the automated way. This is the platform-independent DICOM in, DICOM out pipeline. IB RadTech is a plugin to the ACAN Osirix platform. It's a semi-automated processing application that guides the user through a series of steps that are defined clearly for the user. Both of the first 2 are customizable per your needs. And then finally, if you don't have the resources at your site or don't have the time, we provide FTB processing as a service, and we'll be happy to discuss that with you as well. So please contact us if any of those are of interest to you. The next thing we're going to do is jump into a demonstration using the ACAN workstation and IB RadTech. And before I do that, I just want to highlight that we do have available a tutorial assembled again by Melissa Pra at the Medical College, which helps the users accurately place ROIs on the Delta T1 when doing the semi-automated processing. All right, so this is the deeper dive, a look under the hood, if you will, of the RadTech workflow. Here you see the ACAN workstation available. We click on the series that we want to process, and then we'll go up here and we'll click on the IB RadTech workflow. This menu bar is customizable, so our icons can be dragged up and posted up there for easy access. The RadTech platform is basically a hanging protocol or workflow wizard where you can have different workflows customized to your RadTech template. Mine is quite busy because I've got a lot of development things in there, but we're going to choose the FTB with Delta T1 now. Here you can see that there's step 1 of 7. We have some workflows that are 2 steps, some that are approaching 20 steps, but here it just tells you what to do at each step along the way. So for FTB maps, we require the pre and post contrast T1 weighted image, and we do have a recommended acquisition protocol for DSC imaging. So here in the first step, we are co-registering the pre and post contrast weighted image. We're stopping here and pausing to make sure the user is comfortable with the co-registration. If not, there are some fine-tuning adjustments that can be done on the side to move and tweak the co-registration step, or there's some built-in registration algorithms that you can choose to employ as well. We have optimized the RadTech workflow with what we found to work best. And so we'll just continue on our way here. Once you're happy, you can accept that. And the next step is the only manual step required for the RadTech processing of FTB maps. And all the directions you can see are in here, but essentially we're going to draw ROIs around the region of contrast enhancement. Now, ACAN Workstation has some really cool tools to make this very easy. The sample I've chosen here is a relatively small and self-contained tumor. And you can see here that I am just drawing a rough bounding ROI around the area of enhancement and excluding things such as healthy or common vessels that are not tumor. I know not to be tumor or skull or packing material, etc. And you can do some tweaking with the ROIs that ACAN has. And a lot of this is, again, identified in the tutorial that we have for drawing ROIs on Delta T1 maps. And I captured that area up above because on the next slice, you'll see that explodes into a larger area. And just about done here for the only manual step. Once you're all done with those, you just hit next. The next step is to create a mask using that standardized threshold on the Delta T1 map. So we're applying a quantitative threshold that identifies and creates a mask ROI. And then we will co-register the perfusion series to the T1 plus C image from the previous step. And you can see here we've got a checkerboard, a black and white viewing approach, which is good for the T1 and T1 plus C. It's my preference. Some people choose that for both the perfusion series, but I prefer the red-green viewer for the dynamic series co-register to the anatomical. Once you're happy, you can accept those, and the rest is fully automated, and your database will be populated with the series and the quality output and everything that you want to have. I will point out here that here are the actual voxel counts by threshold. So you can see the cutoff thresholds of 0, 1, and 1.5 6. And so we are done. This is the output that you can, again, customize, but you get the histogram of the output, and you get the report, which contains this tumor statistics. And those means actually are significant, but again, the FTB maps are a much more accurate way to get the spatial distinction between high CBV and low CBV. And then we get the actual FTB map itself with the calculations above in the description here. But I want to point out here the area of orange that I spoke about previously. This is an area that did not have any signal to process. And so instead of capturing it as a blue area and including it in the totals, we just highlight it orange and exclude it from the calculations. So that is, again, there's two ways to create the FTB map. One is with the automated platform that we have. Another way is the RadTech. Again, happy to entertain any questions or reach out to me after the call to discuss FTB mapping. And I guess at this time, we'll pause and just ask for questions. One option too, if you want to analyze a study and send it to us, we will process a case for you and send you some results for your evaluation. But otherwise, it's a relatively straightforward approach now to get FTBs going at your facility. So how to use, the first question I see is how to use FTB for clinical workflow. And that just came across. So again, we have the FDA cleared tools that's available in a couple different approaches in our applications. One is the automated approach, and the other one is using the FDA cleared version of the ACAN workstation as part of an Osiris plugin. Those are the two ways to obtain it for a clinical workflow. And there have been several trials performed using FTB. There is one study going on here, and I think Kathleen Schmainda may be on the call, but it's the Gable study that is looking at DSC perfusion in a unique way. So it's going to be used in a kind of a major study here led by Dr. Dan Baboriak out of Duke. So the second question I see is the automated pipeline durable to changes in the scanners used? Or do the studies always need to be performed on the same machine? No, that is one of the key elements and one of the elegant features of both Delta T1 maps and IB Neuro is that the standardization technology used takes all those variabilities and those differences in scanners, field strengths and parameter settings into account, and so you come up with a consistent and repeatable measurement between time points and field strengths and scanners and et cetera. I hope that answers your question. If not, please let me know. And then finally is the last question I see is, are most users using our SRCBB and what thresholds are being used? Most of our users are using our standardized RCBB. Initially, they started off using normalized RCBB and manually placing that reference ROI, but they found out that as more and more people were doing studies and validating the standardized approach, which is automated, they discontinued using normalized RCBB and adopted the standardized approach, which again is more consistent and repeatable. And I would say that the vast majority of our clients are using the 0, 1, and 1.556, which is what was reported in the PRO study coming out of MCW. But there are several users who are also using the legacy 1.75 cutoff threshold. I think the key is, again, that we will apply whatever thresholds you determine, but do not change those over time, because then you lose the whole benefit of the standardized quantitative approach and measuring how things are changing over time. So I hope that answers your question. Linda, are there any other comments or questions?
Hi, no, I'm not seeing questions on my end, so I think that concludes our webinar for today. I wanted to thank everybody for joining us, and please look for future webinar invites. Thank you, Mike.
Thank you all. Have a good day. Bye-bye.